Section 7.5 is about roots and zeros. This concept summary gives us a lot of information about polynomial functions and some things we can say about them. If you're given a polynomial function, first of all, if we say that c, some value, is a zero of that polynomial function, then we also say that x minus c, that binomial, is a factor of the polynomial function, which means that binomial can be factored out of that polynomial function. We also call c a root or a solution if the function is set equal to 0. Now that's something that we've done in the past where we set a function equal to 0 and we solve for it. This summary tells us that that's called a root or a solution. And then finally, the point c0 is the spot on the graph where the function will touch the x-axis. So if c is a real number, then the point c0 is an intercept for that function to touch the x-axis. Down here you see the key concept which gives us the fundamental theorem of algebra. And that says when you have a polynomial equation that has a degree greater than 0, then it has to have at least one root that's at least a complex number. More often than not, it'll be a number that's not complex, but at least it has to be a complex number. Here we have a number of examples where we have to solve these equations and then tell how many roots there are and what type of roots they are. So we'll start by solving this first one. This one, because it's a first degree, we're just going to subtract the 3 and say that x equals negative 3. So this has one real root because negative 3 is a real number, and that solution is negative 3. This one is a second degree polynomial. Those can be factored. So I need two factors of 16 that add to give me a negative 8. So that's x minus 4 times x minus 4. You could also write that as x minus 4 squared. Now we're going to use the zero product property. And so you get the solution x equals 4, but you get it twice. This is called a double root. But the point is this equation has two real roots. Even though they're the same, we still count them as two real roots, and those roots are 4 and 4. Here there's a third degree equation. I'm going to take out a GCF of x, leaving an x squared plus 2. Using the zero product property, we'll set each one equal to 0. One of my solutions is 0, but the other one I'm going to subtract 2. So x squared equals negative 2. I'm going to take the square root of both sides. So x equals the square root of negative 2. Now remember, we can't have the square root of a negative, so we'll pull out the I, which is the square root of negative 1. And then that leaves square root of 2 in the back, and don't forget the plus and minus. So in this case, we have three solutions, one real and two imaginary. The real one is 0, and the imaginary is positive I root 2 and negative I root 2. Over here we have a fourth degree. This is a difference of squares, so it becomes x squared plus 1 and x squared minus 1. X squared minus 1 is a difference of squares again, so I can break that up into x plus 1, x minus 1. Again, zero product property will set each one of these equal to 0. So the second and third one, x is going to equal a negative 1, and here x will equal a positive 1. Over here, when I subtract the 1, I get x squared equals negative 1, and then I can take the square root. Well, that means x equals the square root of negative 1, which is really I, so we get plus or minus I. So in this case, there's four solutions, two that are real and two that are imaginary. The real are negative 1 and 1, and the imaginary is positive I and negative I. Now if you go down here to the bottom, it says compare the degree of each equation and the number of roots. So go back up here. The degree of this equation is 1, and with 1 degree, we ended up with 1 root. Over here, the degree of this equation was a 2, and we ended up with 2 roots. Down here, the degree was a 3, and we had 1 real and 2 imaginary, so we had 3 roots. And in this one, the degree was 4. We had 2 and 2, which meant 4 roots. The point is that the degree equals the number of solutions, or the number of roots, of the quadratic equation. Now this is going to lead us to this corollary of the fundamental theorem of algebra, which says just what we said on the last slide: the degree of a polynomial is the same as the number of roots. Now there's also a famous idea called Descartes' rule of signs. Descartes was a French mathematician who discovered this little relationship that we're going to see here. And it says that if you plug in an x value into a polynomial, the number of positive real roots is the same as the number of changes of signs on the coefficients, or is less than that by an even factor. Likewise, if you plug in a negative x, the number of negative real roots is the same as the change of signs, or less than that by an even number. So the point is, if you count up all the changes of signs, you can find out how many positive and negative roots there are. That's a very difficult concept to understand unless you see it worked out as an example. So we're going to do that right here. We're going to try to find out the possible number of positive real zeros and negative real zeros in this polynomial function. So we're going to start by writing out p of x with a positive x, and we're going to count up every time the signs of the coefficient change. So here, the coefficient of the x to the fifth term is positive, and it goes to negative. So this is a change in sign. We say, yes, that's a change. Here, this one's negative, and it stays negative, so that's a no. Negative stays a negative, because negative 3 stays a negative 3. Negative 3 changes to a positive, so that's a change in sign. Positive 7 then becomes a negative 8, so that's a change in sign. And negative 8 becomes a positive 1. So that's a change in sign. Which means, according to Descartes' rule of signs, there's either 4 roots, but you also need to go down by an even factor. There could be 2 roots or 0 roots. So you just subtract 2 each time. These are the 3 possible number of zeros that we could have according to the change of signs. The other part of Descartes' rule of signs says to put a negative x in for all the x's, so I'm going to simplify this. If I take a negative and I go to the 5th power, it ends up being negative. So that's going to simplify to negative x to the 5th. If I take a negative to an even power, that stays positive. But the 6 in front stays negative, so you end up with x to the 4th. Here this negative to the 3rd power goes negative, and then you multiply by the negative here, so we'll get a plus 3x cubed. So notice what's happening. All the ones that are odd are actually changing signs. This one here is going to stay a 7x squared. This one's going to change its sign to become a plus. So that's what happens when you plug in the negative s. You change all the signs of the odd exponents. And now you look for the change of signs from each coefficient to the next. So here we have a negative going to a negative, so that does not change. A negative going to a positive, so that's a change. Positive to positive is not. Positive to positive is not. And finally, positive to positive is not. So that means there's going to be 1 0 or 1 root that's negative. So we have 4, 2, or 0 that are positive, and we have 1 0 or root that's negative. So now I'm going to make a table to organize all of this information. The number of positive real zeros, we said from counting the changes of sign, was either going to be 4, 2, or none. Those are the 3 possibilities. We also found out by looking at the changing of signs that there was only going to be 1 negative. Now we know from looking at the degree of the polynomial, there has to be a total of 5. So there has to be 5 on here. So using this chart, we can tell how many imaginary zeros there has to be. Well, if I have 4 and 1, that means there has to be no imaginary zeros. If I have 2 positive, 1 negative, that would mean I need 2 imaginaries to make 5. And if there were no positive and 1 negative, I would need 4 imaginaries. And so these represent the 3 ways that you could break down the solutions or the zeros of this polynomial function by using Descartes' rule of signs. Now in this example, we're going to use Descartes' rule of signs to find out the number of zeros. We're going to use that to actually find the zeros that exist for this polynomial function. We'll start off by listing the function with positive x and negative x, and then counting up the change in signs. So here we have the function with the positive x. Change of signs from here to here is yes. Then negative to positive is yes, and then positive to negative is yes. So that means there's either going to be 3 roots or 1. Those are the possible number of roots, because you've got to go down by an even factor. So 3 or 1. Then we plug the negative x in. I didn't do all the work, but if you notice, each odd degree term has a change of sign. And I told you that in the last example, you just change the sign on each odd degree. So negative goes to a negative, that's not a change. Negative to negative is not, and negative to negative is not. So that means there are 0 negative roots. So because we know the degree of the polynomial is 3, we are either going to have 3 real roots, or we'll have 1 real root and 2 imaginary. So this is what we're looking for. We're looking for either 3 real roots or 1 real root with 2 imaginary. That's what the rule of signs tells us by looking at the change of signs. Now, finding what the roots are is a different matter. We will start by finding what f of 0 is. And we plug a 0 in for this function, we're going to get a negative 4. And that's going to give us a couple of examples or a couple of values to start with. Now, we know that there are 0 negative roots. So we're going to try the numbers from 1 to 4. We're going to try 1, 2, 3, and 4, see if we can't find the 3 roots. And the way we're going to do that is by using synthetic substitution. Now in this slide, I'm going to go and do all the work for the synthetic substitution. I'm going to get it all up there, then I'll go and give you a brief overview of what the synthetic substitution means and how we can use the information to find the roots. So here you see all the work for the synthetic substitution. Remember that we decided to try the numbers 1 to 4, and so over here represents me trying 1, 2, 3, and 4 by using synthetic substitution. So when I do that, I found out that there was a remainder when I tried 1, 3, and 4, but when I tried 2, there was no remainder. The remainder was 0. So 2 we know is one of my solutions. Now here's the beauty of using synthetic substitution. If I would have used just regular substitution and plugged 2 in, I would have found out that it equaled 0, but I would not have gotten this depressed polynomial. And that depressed polynomial, that x squared minus 2x plus 2, because that's what these numbers represent, they represent the coefficients, that new depressed polynomial can then be used to find the 2 imaginary solutions that I have. So I'm going to go back here, and I'm going to say that one of my solutions, x equals 2, I found that on the last screen, but now I have this new depressed polynomial, x squared minus 2x plus 2. Now how can I solve that? Well, it doesn't factor at all, so I'm going to use the quadratic formula. So here's the quadratic formula if you don't remember, and I'm going to plug the values in. This is a positive 2. Underneath I'm going to get a 4 minus an 8. So all this stuff underneath the radical is going to be a negative 4, and that's all over 2. Now we can't have the square root of a negative, so this is really a 2 plus or minus I, because that takes out the square root of the negative 1, times the square root of 4 over 2. Now we're going to continue to simplify that. I'll go up here and do it. So that's 2 plus or minus I, and the square root of 4 is just 2. Now I'm going to rewrite that as 2I, because that's typically how we're going to write it. Now this represents 2 plus 2I over 2 and 2 minus 2I over 2. Simplifying one step further, I can take a 2 out, leaving 1 plus I over 2, and then cancel the 2's. Same thing over here, take a 2 out, 1 minus I over 2, cancel the 2's. So that's going to leave me with a 1 plus I, that's one of my solutions, and a 1 minus I, that's another one of my solutions. So you can see here, my solutions were 1 real and 2 imaginary, which I said was one of my possibilities at the very beginning, by doing Descartes' rule of signs. In this example, we're asked to write a polynomial function if we're given the zeros. So here we're given a 3 and a 2 minus I 0. Now for this example, we're going to need something called the complex conjugate theorem, which says that if you have a complex conjugate that has an addition sign, then the one that has the subtraction sign is also a 0, and it works vice versa. So what we're saying is if we have a 0 that's a 3 and a 2 minus I, because of the complex conjugate theorem, we also have to include the 0 that's a 2 plus I. So really there are 3 zeros in this problem, and we're going to have to write what the least degree polynomial looks like. Well, here's how to do it. Because of the concept summary at the very beginning, we know that if each one of these is a 0, then that means x minus 3 has to be a 0. That also means that x minus 2 minus I has to be a 0. And likewise, x minus 2 plus I has to be a 0. Because whenever you have a 0, that means the polynomial x minus that number is also a 0. So we're going to simplify all of this by multiplying it all out. Well, we're going to leave the x minus 3 alone because that's the easy part. But inside of here, I'm going to use brackets. And I'm going to take the parentheses and I'm going to move it around the x minus 2. And that's legal to do because that's just the associative property at work. And then over here, I'm going to move the parentheses so it surrounds the x minus 2 also. But this time we'll have a plus I. Now looking at the two bracketed areas, this is actually a difference of squares format. And I'll write it up here in case you forget. A plus b times a minus b creates a difference of squares, an a squared minus b squared. That's one of those special products we learned way back in algebra. So because I have that, I can now take the x minus 2 and square that. And 1 plus and 1 minus is going to simplify to a minus, and then I have an I squared on the back. Now continuing to simplify, x minus 2 squared is x squared minus 4x plus 4. And minus I squared is just a negative 1. So all of that becomes x squared minus 4x plus 5. And now I'm just going to use regular parentheses because I'm multiplying that still by the x minus the 3 in the front. Now I'm going to use the distributive property here. X times x squared is x to the third. X times negative 4, negative 4x squared. X times 5 plus 5x. Then minus 3x squared plus 12x. And the negative 3 and 5 is minus 15. We start with the x to the third power, and then we combine the minus 4x squared minus 3x squared into minus 7x squared. And then we have plus 5 and plus 12 is plus 17x minus 15. So our final answer is the function that has those 3 solutions that I had up top, 3, 2 minus I, and 2 plus I. The function that has those 3 zeros or roots is x cubed minus 7x squared plus 17x minus 15.